So let me introduce our next speaker, Krishnamurthy. And he's going to talk about basics to Benchtop.
Okay. Thank you, Dave, and thank you, everyone. I continue to have the pleasure of standing between you and the drinks that's going to be coming up soon.
There?
Not yet. Not yet. I'm holding it. I'm holding it. Okay. So I'm sure I'm going to be open. I'm going to be 70 today. Not today, this week, this month. No, this year. In any way, the reason I announced that was throughout our life, there's going to be a moment in our life that change our happiness. I'm sure all of us have. We probably don't want to say anything, particularly when it comes to professional life. And it happened for me as well. 10 years ago, October 31st, I have fired the entire management team that is telling me what I am supposed to do and became myself. I'm having so much fun learning basics of NMR. That's what I want to talk about. It was an involuntary firing, just so you know. Just so you know. Seriously, I think it gave me the opportunity to funnily sit in with a glass of wine, watch the TV or pretend to watch TV and think about why we do what we do. So that's what I'm going to talk about today. It's a continuation of several talks that I have given in Ivan conference. So it will be a continuation of that. If you are interested in looking at the previous ones, you can certainly see our YouTube channel to do that. So first, to start with, I want to talk a little bit about definitions. Definition meaning, what do I mean by time domain analysis? And I say also known as crafts, that's simply because I use craft, which is a tool somebody developed that is a time domain analysis tool. And beyond that, there is nothing else that's implied there. I'm going to talk about time domain analysis. What do I mean by time domain analysis? So here is an example, a cartoon of a tabular time. I introduced this tabular domain, frequency domain analysis domains. We all know about this time domain. We do FT, we think about frequency domain. What tabular domain is where you have a table of frequency, amplitude, decay rate, phase, or some derivatives of that, coupling constant, chemical shift, whatever you call it. It is the derivative of those four basic parameters of NMR. And when I define frequency domain analysis, I'm talking about taking the frequency domain information down to tabular domain. That's a frequency domain analysis. We see a lot of studies have been done, so many years of development has been gone through. What I am talking about time domain analysis is going straight from the FED to the tabular domain, because the FED is a linear combination of several sinusoids, a linear combination of sinusoid, each one being described by a frequency, amplitude, decay rate, phase. And tabular domain is the FED. So is there a better way of doing this? It's not just about the better way. That is what I mean by time domain analysis. All the analysis that we do, whether we like it or not, whether we accept it or not, whether we admit it or not, are in tabular domain, either in a piece of paper or in napkin or in your brain. You're still thinking of numbers. Frequency domain is a visual representation of that number. That's what we are analyzing. So one level down, what do I mean by time domain analysis? I go from FID to table, and then I apply all my NMR rules. When I say NMR rules, I am a trained synthetic organic chemist who thinks in terms of chemical shift, coupling constants, structure, methyl group, ethyl group, and so on and so forth. So I apply all that, my learning, and then generate a table that is more chemistry friendly, chemical shift, amplitude or integral or line width and phase and so on. And then I can look at a spectrum if I want. I don't have to look at spectrum because from the tabular domain, I already can interpret, right? That's the idea of this time domain workflow, time domain analysis workflow. So here is an example. This is a benchtop symposium. So I'm going to have benchtop examples, but many of the basics are the same, whether it is a benchtop NMR or high resolution NMR. Here is an example of a benchtop spectrum. So your frequency domain, your FT would have given you this blue line from FID. In craft or time domain, we would have converted the time domain into tabular domain, and the tabular domain has this offset decay rate phase, which describes that entire FID in a tabular format. So the spectrum that I see is not anything from the FID, is not anything from this spectrum. It is just a simulation of that table into a representation that you and I like to see, because we are visual creatures. And the residual is really difference between the two, not in frequency domain, not in spectral subtraction, in taking this time domain, taking this tabular domain, converting the tabular domain back into time domain type of information, because it's a linear combination of all these sinusoids, and then subtracting these two, and then visualizing the spectrum of that residual. So it's really all works in either time domain or in tabular domain. But I'm going to use a lot of spectrum. Just wanted to alert you, anytime, unless otherwise I specifically say it is a Fourier transform result, none of the information comes from spectrum. None of the information comes from spectrum. They all come from the FID itself, directly into table, and then we do the analysis. And then any representation is from that. So I don't know why I have this information. Why I have this, now I know why. I just wanted to emphasize the point. Spectrum is a visual representation of a table. It's almost like a pie chart versus a spreadsheet. Spreadsheet has information. Pie chart is a visual representation. That's what I wanted to emphasize in that table. So in this, but in the previous, if I can go back. So in the previous example, where I took the tabular domain to the craft result, I took this step, that table, and represented that. So it's just a sum of all of that. But I don't have to do that. I can apply my chemistry knowledge or NMR knowledge and then look for the peaks of interest. Again, I'm not looking at the spectrum. Remember, I said FT, unless I specify that it is FT, all of this coming from the table, just represented in a spectral format, just so you and I can see. So when I say I'm interested in this peak of interest, which is that shoulder right there, and then I am not interested in these peaks of interest, all I'm saying is taking that table and then say, hide this row, emphasize this row. It's a spreadsheet, right? And then I can look at it, and then I can say, what is the amplitude of that? In this particular example, interesting example, this is again a 60 megahertz spectrum, I think. In this particular example, this is a C13 satellites. Those two, I deliberately kept the C13 satellite of the primary peak. And then I said, that is a C13 satellite. I can actually look at the amplitude of the C13 satellite, not from your spectrum, from the table. The table came straight out of the FID. Yeah, so that is 0.55 to 0.55 to 98.5. So it is you have an internal confidence in there. And what we are looking at in terms of the quantification of that peak is 8,000 to 1. And that's exactly what it is, because it's supposed to be 200 ppm spiked, and then this is supposed to be 4:1 ratio, and so on and so forth. The point being, if you are working in tabular domain, you can take a peak, reject it, accept it. Suppression, no suppression. Water suppression, solvent suppression, just reject that peak. From a table, that's gone. So in this particular case, this huge peak there, reject it. Don't represent, you don't care. And you can get rid of that. So this is a kind of workflow that you have if you are working in tabular domain. So I'm coming back to basics to Benchtop. Over the period of the last 5-6 years, I have talked about line shape. I talked about sensitivity. I talked about resolution. We redefined what we mean by sensitivity. Resolution in 1D, resolution in 2D. This is actually not 2D, but that's also, we gave 2 seminars on this. And then we also talked about oversampling. So today, I'm going to go further out. I might come back to sensitivity and all that a little bit, but I'm going to talk about noise. I'm going to talk about shimming. I'm going to talk about phase. Okay, back to benchtop NMR. This is an HSQC spectrum. One is 64 increment, another one is 128 increment. Fourier transform result, FT2D result, conventional processing, whatever you want to call it. Expected way in behavior. 64 looks terrible, and we ask the question of, do I need to do 128? Should I do 512? Do I have enough resolution? And so on, so on, so on, so forth. Do I have a narrow peak? And so on, so forth. Whereas when you analyze this in tabular domain, those are the 2 spectra. The projection here is not a high resolution spectrum on the very top. It is actual projection of that 2D representation. Right? So this resolution here, the positive and the negative peak resolution there, they are all real. I just projected it. It's a skyline projection. It's not even skyline, it's a sum projection. So the first question we have to ask ourselves, and we know, when I say we know, we think we know, is, oh yes, of course, it's a 64 increment spectrum. I have this T1 noise. We heard that. We have this T1 noise, so you increase your number of increments, it goes away. It becomes less and less. So, Krish, you are cheating. All you are doing is plotting at a very high threshold level. No, that's not what I'm doing. Let's take a look at what is noise. So in the past, we typically tend to, a lot of us, when we give a lecture about signal and noise, we typically tend to talk about that. There's a signal, which is a sinusoidal function that's coming from our sample, and then there is this noise. And you are trying to find out how well you can get this signal out of this noise. That's not really it is. So this is signal. This is what you are detecting. It is noise is on top of the signal. So then the question is, so okay, yeah, noise. I get that. So the question I have to ask is, what is noise? What is physically noise? So let's take a look at an expanded region. The front end of the FID. This is actually an interferogram. Front end of the FID. Let's take a first look at this blue line. That is the acquired FID. Yeah, and this is the sinusoid that I see on this. I can actually see. I don't have to do anything. I can see a sinusoid there. I can draw a sinusoidal function in there, and that's the difference between the two. So when I say noise, what we really mean is that there is nothing physical. It is about how certain you are in the time domain data points. How certain you are. So noise is nothing but uncertainty in the signal detection. That's the definition. Uncertainty in the signal detection. So the very moment I say uncertainty in signal detection method makes a difference. Depending upon your detection method, the same data may give you a higher uncertainty than one method and less uncertainty in another method. So but the very definition of noise, we actually now we introduce a noise means, how are you detecting the signal? In this case, how am I detecting the frequency? In this case, yeah, how am I detecting that oscillating sinusoid in there? I can visually even do that. Mathematically, it's trivial. And so this is the noise, that is the uncertainty in there. So when I look at the frequency of that, it simply says, I'm putting it in chemical information, which is in ppm. It's actually an offset, but I'm putting it in ppm. It says, I can detect a sinusoid 77.689 ppm at the accuracy of 2.4 hertz. This is a mathematically Bayesian analysis of this FID, which is this FID. Bayesian came back and then said, that's a sinusoid I can see. And the accuracy of that sinusoid that I am probability that I am predicting is 2.4 hertz. So that is the uncertainty of that frequency. So if that is uncertainty of the frequency, what is uncertainty? Uncertainty is line width in some way, because there's no decay here. I'm looking at the very front end, 64 increments. There is no detectable decay in 64 increments. So if you don't have a detectable decay in 64 increments, what is the line width in your 2D represent along parallel to F1? It's everything that you do to get to that picture. It's not there. There is no line width. There's no decay. I can't see a decay. You can't tell me that there is a decay in 64 increment, which is 80 milliseconds. Carbon. Detectable decay is not there. Particularly if you are dealing with a constant time experiment, there is no decay. That's one of the beauty of constant time experiment. So in some ways, when we say that there is a line width in 2D, we actually mean there is an uncertainty in the frequency measurement that I have. That's because my methodology is poor. Whereas when I do it in time domain, when I do time domain analysis, that frequency error is in hertz. So here is what I can do. But you can say that, hey, you're throwing away the uncertainty information. No, I'm not throwing away the uncertain information. What I'm taking is, I'm taking this interferogram, convert it into a table, and then there is this box. I'm sorry, this is very poor in terms of font size. There's a box called F1 width. That's actually the plus minus uncertainty. So if I represent that uncertainty as a line width, which is a distribution of frequencies, then this is a spectrum that I get. So I did not throw away the noise. I just represent the noise differently, which is the uncertainty of measuring that frequency. Nothing more, nothing less. So there's no T1 noise here. T1 noise, that read came because you did an FT, not because it was something real. You did an FT of the uncertainty, which is the top trace in the three trace picture that I showed you. Right? There's more. There is more you can do with it. This is an interferogram that I represent that. I represent that as a 2D because I said I'm going to keep it 1K by 1K transform because it becomes very big data set. That's a 2D. What is preventing me in saying that no? Show that because my uncertainty is 2.5 hertz or 5 hertz or 10 hertz in ppm scale. I can represent that in a 32K complex transform. In a 32K complex spectrum. That's a depth spectrum. That is a high resolution selective depth experiment coming from 64 increment HSQC. Nothing else was done, no experiment done. All I did was I analyzed it differently. Not do FT. Not from, I don't want to say not do FT because this is FT. I did an FT to get to this picture. Not rely upon the frequency domain data to extract that information. Rely straight on the time domain data. In fact, I can even go further out. That is a depth experiment. That's a depth result. 64 increment carbon. That means there are only 64 points in the carbon dimension you collected. And these are the two carbons that you can resolve. Those two carbons are separated by 16 hertz from each other. So now if I come back to this and then say, this is my time domain analysis of the same data as this. This is the time domain analysis of the same data as this. the noise is not lost, or the uncertainty is not lost. Yes, this is more uncertain because the average frequency error is about plus minus 0.15 ppm. This is average frequency error, is half of that expected. But if I put them all, if I plot an amplitude of one against the other, it's exactly the same. I have a slope of 1 of all the cross peaks there. What did I gain by going from a 64 increment data to 128 increment data? Nothing. Except my certainty of my frequency is improved. At what level? In less than about 10th of a ppm level in carbon dimension. So we are wasting our time. We are wasting our time if we decide to run more than that. So the question we have to ask ourselves, is there any benefit to do higher number of increments? If you can, two-dimensional NMR was invented long time back to separate frequencies, magnetization in two different frequency dimensions. That's exactly what we are doing here. That's exactly what we are doing here, except we just threw it away by transforming it by FT, and then we apply all the window functions that we have to, because if I zero fill, I get these sinusoidal artifacts, and I need to do a Gaussian multiplication or a sine squared sine bell multiplication. Whatever you care, I don't care what you do. You are just multiplying and broadening your peak. So the question I want to ask, this is a benchtop group. How about we do a benchtop? I do an ASAP HMQC and Craft 2D. Analyze that. What do I mean by that? If I can do an ASAP HMQC in 1 minute acquisition, this is not a benchtop data. I'm just questioning this now. If you have this kind of a 1 minute acquisitions, then if you can process in less than a minute, that means you can kinetically, if a reaction is happening, you can follow the reaction at a minute at a time. The reaction, the product, if assuming this is just an example, the product and the reactant typically are close to each other. They are structurally similar. Maybe you are doing a reaction where there is something happening somewhere else. You can even follow a carbon at 6.28 and a carbon at 6.08 with their amplitude. You can follow that amplitude at that resolution. There's nothing stopping you from doing that. Now, a good friend of mine, long-term colleague, a convert, a baptized convert, Andreas Kerner, came up with this interesting idea. You don't even need to run 1 minute acquisition. You can now, this continuous, he hasn't published it yet, but we have talked about this about 8 years ago. You can actually now follow reactions at increment time level. If you can analyze it that fast and that reproducibly and that much automated. And this is 4th increment. This plot that you are seeing in here is every 4th increment you are following the time course. You have an opportunity here, not because it's not there, it was there. As I said, at the front end of the fin in a carbon dimension, there is no decay. So it should be a sharp line. The only line width you see is actually the uncertainty in your frequency position. Now I want to talk about line shape. We heard a lot today about line shape. Yeah, line shape, this is a typical target line shape. I'm an old timer. I don't know what the current line shape specs are. This is the typical specs that when I was in the applications lab, this is what we try to meet, 0.6/6/12. It's a typical line shape we try to meet in high resolution. As I said, line shape is line shape. Whether it is benchtop or not, it's a line shape that you are trying to meet. And here is 2 examples of spectra. One is line shape, width at the half height is 1.38, width at the half height is the same in both cases. In one case, the width at 0.55 is 10 hertz, here it is 20 hertz. Naturally, this is taller, this is preferred. In most bad or poor way of describing it, this is better shimmed. It is not. I'm giving you the answer. It's not better shimmed. I'll tell you why. So we think we better shimmed. All right, because it's taller, narrower, I can resolve one from the other. Another way we look at line shape in the real world, every time you don't run chloroform, is look at the TMS. If you have the TMS or some peak, in this particular case, I pick TMS. I put the TMS in there, and then this blue line is a vertical scale blown up, and then I put the cursors on either side of the TMS, equidistance, and then say, do I have a symmetrical pattern there? Does it look symmetrical visually? I'm looking at it visually and say, yeah, that looks symmetrical. That looks good. So and then I look at the line shape, and then the line shape says 0.93 for 50%, and 50.55 is 9.69, and 0.11 is 14.06. I'm happy because, well, degassed chloroform, I convince myself in a degassed chloroform, if I can do 0.6 over 6 over 12, TMS looks good, symmetrical. I see a 914, I really narrow on the bottom, and then I have silicon satellites. Oh, that's because my 0.9, this is 9.89 is because I have silicon satellites. I can't measure inside the silicon satellite. So I convince myself that that is the best shim I have. It is essentially wishful thinking. Because I am convincing myself because I want to finish the project and go home. I want to finish the project and go home. Now, what if I want to take this? This is well shimmed, meaning very homogeneous. This is the biggest correlation fallacy that we have. Just because it is a narrow peak doesn't mean it is homogeneous. I take that peak, that TMS peak, and then tell Bayesians, rip it apart into as many curves, exponential decay functions as you can to describe it. It is the same TMS peak. Bayesian came back and then said, well, you know what? I have to describe by this many exponential decay functions in order to describe it. So you can actually see this is the FT result, that's a simulated result, the residual. And these are all the individual components that I need to, I'm not telling Bayesian that it has a singlet. I'm just telling Bayesian, I don't care. Just tell me how many peaks there are, how many exponentials are there. So this is what it has. What it should have had, I don't know why I have this. There's no precondition. That's why it is there. There's no precondition. I'm not saying that it's a singlet. I'm just saying just fix as many exponentials as you need to describe it. Okay, so this is a problem that we face. So something is missing here. So the resonance model, and here I'm just saying the goal is not to define a peak as a singlet or a doublet. The goal is to define the peak completely. Why exponential? All NMR decays are exponential, irrespective of whether you have a homogeneous field or not. When you don't have when you have an inhomogeneous field, the peak on the top of your NMR tube decays at its own fashion, exponential. If magnetization, a spin at somewhere in the middle of the NMR tube, decays its own, because that's what it is. It's a free induction decay. It's first order kinetics. Fundamental basics, yeah. Unless you're doing something in the middle of the acquisition, then all bets are off. You're not doing anything in the middle of the acquisition. It's just a free induction decay. So when I say describe it, it describes it like this, as an example. This is a different example. So what is a problem? The problem is the line shape. When we said line shape is 0.6 over 6 over 12 is a spec, that's not a Lorentzian spec. I got this picture, Google. I just go type Google Lorentzian line shape. What am I supposed to have? In those days when I was an applications chemist, I didn't have Google. I trusted that 0.6 over 6 over 12 is Lorentzian. In fact, in principle, I was under the impression, this is honest to God truth. I was under the impression, line width at the half height times 10 is 0.55, times 20 is 0.11. That's my rule of thumb. But Laurentian is supposed to be 13 and a half times LWHH. At 0.11, it should be 30 times LWHH. So really, more often than not, pure Laurentian is actually an exception in your spectrum. You are over-shimming, meaning you are actually, when you say you have a narrow peak, you are actually made it inhomogeneous. It's inhomogeneous so that the ensemble looks narrower when you do an FT. So visual is what we did. It's not homogeneous. Shimming is not, doesn't mean it's a homogeneous field. What should it have been if it were homogeneous? It is this is TMS. If I take the same region and then I say, yeah, this is a TMS, I have a silicon satellite, I know the isotopic ratio, I can assign a certain amount of amplitude, I have some C13 long range coupling that has some amplitude, that's a quartet because it is coupled to a C12 proton, 3 bonds away. It's a quartet. So that is again, I'm going to assign amplitude, and this is what I am supposed to get, theoretical. Theoretical line shape of a TMS should be there. So if I had directed Bayesian or directed a time domain analysis tool to fit the input FT, input FID to this theoretical and give me the best fit that you have, meaning that I am directing it to do what I want it to do. This is the result you're going to see. Look at the residual. So invariably, it's true not just about NMR, it's true with everything. Attempting to fit an observation that is not a linear combination of your model is always a compromise, whether it is a weather prediction, whether it is a stock market prediction, or whether it is NMR or FTIR. The moment you say this is an exponential decay, fit it to exponential decay, your input better be a linear combination of that. If not, you have a compromise. You simply asked it to direct. If I were weather prediction, I have a Sharpie, I can make the weather go anywhere I want, right? That's a problem we face. So this is the blue one is the observed input FID. The black one here is a theoretical TMS. The red one is the observed TMS in mathematical fashion. So if I take the blue times black over red, I will get the pink. That's exactly what Fiddle does. This is not something that we invented. This was invented and has been around for 30 plus years. Gareth has done this long time back. Essentially, you take your TMS or some reference signal and then say, this is what I am expecting that signal to be. And then you take the ratio of the two, multiply the entire FID with that ratio, with that time domain. That's it. You correct your non-exponential FID into exponentially decaying FID. This is where free induction decay deconvolution for line shape enhancement. Fantastic acronym yet again. Now in Kraft shim, how do we do that in time domain? Remember, this is done in 1988. It was done using frequency domain. He actually takes a spectrum. You snip out that area, do an inverse Fourier transform, and then fit that to a expected singlet, and so on, so forth. But we can do it in a slightly little bit more fancier fashion. So because if I go back to my equation, this black line here is my theoretical TMS model, because these are all the models that adds up to that. The red one is observed TMS model. These are all the models that's observed. These models came from Bayesian analysis of this blue line. So one is a theoretical TMS model, another is observed TMS model. I can actually look at it from a tabular format. I don't need to look at it as frequency at all, frequency domain at all, not even FID. These are the models. This actually one line represents each one of the blue one. Each line represents a model. And then that's my experimental model or observed models. And then I sum them all up, vector sum. Add them vector sum and says, okay, you have a amplitude weighted center at 2,300 hertz. Right side, that's the amplitude, that's the decay rate, that's again amplitude weighted center of the T2 star, and that's a phase. So I now have a vector sum that represents TMS. Except I now know TMS has, this is what it's supposed to be. And I know what the ratios are. I can simply distribute that amplitude across these theoretical models. So I have a table that is observed model. I have a table that's a theoretical model. I can take a ratio of the two. I'm not looking at the FID. I'm not looking at the spectrum. I'm just looking at the table that came from the FID. And then I'm fitting that to a theoretical model. So then I can do the same thing. So the picture I showed you there is not about fiddle in the conventional way. This is the fiddle in the craft way, meaning that I'm just doing fiddle correction factor based upon the models that I give. This is what Dan Iverson alluded to. We have a fiddle CF as a function, which you can synthesize. You can take any two synthetic models and then say, give me a ratio of the two. One is observed models. The other one is theoretical models. Now comes the question of benchtop. All right. In the conventional fiddle, you typically need about 60 hertz plus minus around your reference peak, clean, well separated, isolated signal that you need in order to define what it's supposed to be, whatever that is supposed to be. Now, I'm not saying TMS is the one to go. I'm just saying, whatever it's supposed to be, you need a clean area. Benchtop NMR, 60 hertz on a 60 megahertz is a 1 ppm window. I don't have the luxury of 1 ppm window. But when we do it in a tabular domain, I don't need a 1 ppm window. All I need to do is a defined peak that I can generate a model of. It can be a peak somewhere. It can be a component of your doublet. In this particular case, it is the component of a doublet of a doublet. I don't care. As long as I say, yeah, that's a peak, it's supposed to be a singlet because it's one of the multiplet components of a large multiplet. That's supposed to be a singlet. It's supposed to be a single exponential decay function. I can do the same thing. And then we will talk about how I compare those two downstream in a minute. So these two give the equivalent result. So in Kraft shim, which is an equivalent, which is nothing but an extension of fiddle, we are not constrained by an isolated proton. We are constrained by being able to define something as a proton good enough with conventional good signal to noise in the conventional signal to noise, meaning white noise, so that I can define that peak observed models in a very, very good confidence. That's all that is needed. So good signal to noise, conventional signal to noise is all you need. It can be any proton or any signal. In this particular case, it's actually one of the doublet of a doublet. Yeah. So how does it affect the result? Here is a no Kraft shim, no nothing was done. This is a doublet. This is actually a strychnine, very well known proton, H8 proton or something like that. I think if Gary is around, he'll probably tell you exactly what that proton is. That's a proton that comes out of that TMS, which we thought is very symmetrically looking TMS that Chris should have walked away as a well-shimmed spectrum 20 years ago. Yeah, but that's the model that it describes. I put a Kraft shim on that. Oops, sorry. Put a Kraft shim on that. That's what you see. Those are the models it describes. is actually a two very, very small coupling there. That coupling, FYI, is less than the acquisition time, 1 over the acquisition time. In other words, you can actually resolve this. We talked about this in one of the earlier lectures. You can actually resolve that are not resolved in the conventional FT fashion. You can resolve in time domain analysis fashion. I am using Bayesian. It doesn't have to be Bayesian. Some good mathematician can come in and then give me something better. That's okay with me. Because we are now relying upon the uncertainty in fitting that sub FID into number of exponential decay models. So once I do the Kraft shim, it's actually a doublet of a doublet. The coupling constant is much, much, much smaller. Now we say the rule is deferred. The rule is opposite. I am observing something. I'm observing a doublet of a doublet. 1:1:1:1. Go find a method, experimental method to prove it. I am now challenging the experimental guys to prove it. Not because you can't come back and say, I can't see it in a cross-peak. You don't have a method to describe this small doublet. But the fact is, now if you think about mathematically fitting a high resolution spectrum into a quantum mechanical model, and then use that to simulate a low field spectrum, the input is this, can be this, not this. Now that doublet information is provided to that quantum mechanical model. So you have a higher resolution, potential opportunity exists to improve things that you are typically used to. You assume it's a doublet. It's a doublet. Your FT tells me it's a doublet. I'm saying that it is not. It is actually a doublet. The information exists. Use this information in any other methodology. This is not the only example. This is another example that no Kraft shim is spectrum looks like this. With Kraft shim, the spectrum looks like that. It's the same data. It's the same data. Before I said there's a blue spectrum and a red spectrum. I said this is taller, so it's better shimmed, and this is narrower. It is poorly shimmed. Guess what? This is what we call the poorly shimmed spectrum. It's not poorly shimmed. It's very well shimmed. That's why it's homogeneous. In fact, it came from the blue spectrum after doing a fiddle, Kraft shim. So it's homogeneous. That's why all lines are Lorentzian. Homogeneity, NMR, is your magnetic field is homogeneous. That means all your spins in the NMR tube should behave the same way. I'm sorry. This is our basics. That's what we were taught in NMR 101. Now comes, how much time do I have? Almost done, huh? Okay. Okay. So you guys are all going to come back to me. How do we evaluate? All of these things are all hand waved. How do we evaluate? I am going to talk about 1 or 2 slides and then skip, and then we will talk if you guys have more questions. One of the most common things that I notice over and over and over again, including myself not too long ago, is use the residual as the quality of your computation. If your computational information, computational data, and the observed data, which is the blue line, and the Kraft line, which is the red line, if I subtract one from the other, I should have no residual. Yeah, we use this everywhere. I actually put a question mark. I think this is supposed to have a slide that has all kinds of animation, but really? Is that what we are going to use? So let me ask the question of, how are you going to measure that? I want to measure how good you are. How good is that residual is, or how bad is that residual is. I want to measure that. I want a number which tells me how good or how bad it is. How do we measure that? Are we going to do integral? Then what about phase? What about baseline? That's a residual, remember? It has all the baselines as your input FID. How do we measure that? Phase, or is this the error that you're seeing in there? You can see the error there. It's a residual error. Is it phase error? Is it amplitude error? Is it a frequency error? What error does it represent? We don't know. We don't know anything. All we know is, I don't like that residual. I'm not saying it's a bad residual. I'm just saying I don't like that residual because it bothers the hell out of me. Right? Now, so what I did in this particular example, I sort of moved my frequency. I knew this frequency. Just keep telling you the why. I moved my frequency in small scales. And every time I subtracted. Guess what? If I move the frequency by about 0.4057 ppm, 4057 ppm, in parts per trillion scale. If I move it to that level, I can get perfect visually, a residual that I like. Guess what? That is less than the digital resolution you typically began with. So this is within the uncertainty of your input data. So is this a bad residual? Why? It is less than the input uncertainty. So residual is a very bad measure of a methodology's quality, at least in this case. To me, it again, I can sit there and describe how this all happened, but that's what it is. Residual is bad. What we really need is some parameter or something that I can quantify and then say, this is what improves when I make a change to my algorithm. So I need a tool. So I went back to, guess what? Phase. The problem with using phase is, what is the expected phase? This becomes a challenge. All our phase corrections are 2-point phase corrections, at the most 3-point phase corrections. We put our cursor on one end of the spectrum, phase corrected, and call it a 0th order, pivot against that on another end of the spectrum, phase corrected, and then say, that's my first order because I'm pivoting out of this. And we say, beautiful, I phase corrected it. All you did was a 2-point correction. You need a lot more to get your confidence level up. I am sorry. You rely upon the fact, which is truth. You rely upon the fact your phase error is linear. And you simply said, that's linear, but I don't know how to do every one of them independently. I'm just going to take 2 points and then do it, and then trust that. That's a problem. Why is it a problem? Here is 2 spectra. Exactly the same FID, 2 different phase values. You tell me which is the right phase, which is the wrong phase. I don't even know now. They are almost 20 to 30 degrees off. It all depends upon how crowded your spectra is, which is a common problem in benchtop NMR. Your spectra is crowded. So when you are visually looking at a phase and then do a correction, you are bound to make error. You're bound to make error. They are all crowded in that small region. If you now look at the ppm scale, you realize that it's a proton spectrum. It's just a 100 ppm spectrum. That's it. So the moment you say, I'm going to use phase as a measure of my quality, the question is, what is the phase that you expect? So that I can compare for the phase I got against that. And this is where we actually developed an algorithm and all that. We have that many points out of that spectrum you can develop. I'm going to skip all this because the drink is waiting. We will sit down and we can talk about that. way out, almost done. If I direct at the very early, one of the early slides, I said, pick a peak. This is the peak I want. This is the peak I don't want. If I target the peaks of interest, in this case, this is strychnine. I know each proton as well as anyone can know. Or I just go on and pick up the paper by Gary Martin or Christina Thiel. I know all the chemical shifts, right? If I direct and then say, go, these are my protons, what's my expected phase and what's the observed phase, and can you give me a quality factor? Whether I shim it or not, it's going to give you the same number. So the shimming could not be used in a chemically directed because I'm a chemist. I looked at that structure and I said, this is the proton. I didn't say that is four-line pattern. I simply said that's a proton. So the moment I directed, I am biasing all the problems that we had with poor shimming, biasing simply because I am biased. I want it to be strychnine because somebody took a bottle of strychnine, made a sample, and ran a spectrum for me. 20 years ago, I haven't run a spectrum myself, George. Somebody ran a spectrum for me. I trust that person. So I am biased. I want that to be strychnine. So I'm directing this to be. So we have to be very careful. But what if I don't direct it? I do it automatically. I want to do it automatic segments. I want the system to do the analysis. This is what we were talking about when Susie came and talked. When we say automation, we talk about these are the things that I do, including, not limited to, what my structure is. And how do I automate? That's a wrong way to go. It's not a wrong way to go. It is a poor way to go. It's a scapegoat because I know better. Your automation should be completely blind to who is clicking that button. Whether I click the button or my son, who had nothing to do with NMR, nothing to do with chemistry, clicks that button. It should give me the same result. I'm sorry. That's the way automation should be. Right? So this is the automated system. In this particular case, I'm going to skip a lot. In this particular case, okay. I have a lot of things to talk about. I wanted to talk about T2 star. I want to finish up with the last example of what we can do with it. So in that case, you can use the Kraft shim results as a guide to how good is your shimming is. This is, we just had a time domain discussion, time domain NMR, TD NMR. I wanted to make sure that's a TD NMR. I'm talking about time domain analysis, NMR discussion. So here is a FID, synthetic ID. And if I Fourier transform this, I get this. I get it's a 5-line pattern, a quintet, and a triplet. There's and a doublet. There's a doublet there. There's a quintet there. How do I know? I know because I synthesized it. That's a synthetic spectrum. I added a triplet, I added a doublet, and I added a quintet on top of each other and generate me a spectrum. So what is this? That's actually analysis, time domain analysis. When I say time domain, frequency, amplitude, decay rate, phase of this FID, the one in the bottom, after I shift 100 points at a time. So the first line is a FT result of 0 shift, no dwell time shift. And then the next one is 100. Actually, that's 100, maybe less than 100. I don't remember now. X number of points, X number of points shift. Guess what would have happened? My phases would have gone all over the place. Yeah? That's what happened there. The second line there is as though I collected the data 100 data point later, 100 microsecond later, if it were a 1 microsecond dwell time, yeah, later. And then another 100, another 100, another 100. Guess what? That is, if you just look at only the amplitude, that is your decay. That is a rate of change of amplitude because I'm going from dwell point 0 to 100, 200, 300, 400, 500. That's a decay of my amplitude. The problem with this data is it's all phase convoluted because every time you move, your phase rotates. But guess what? In tabular domain, phase is a number. Phase is just a number. I can take every model and then simply add that. It says that's what the phase of that model is. I say, okay, apply that phase. So then this is what you actually have. This is an amplitude. This is not just some CPMG experiment. This is the amplitude of that FID as a function of dwell time. Now, no CPMG experiment. It's a 1D FID. 1D FID. I got an exponential decay amplitude. If it were a single proton, if I do a T1 analysis, exponential fit on this, it's going to tell me that, yeah, you have only one T2. Guess what? This is deliberately a synthetic spectrum. There are two T2s there. One is much narrower, the other one is much wider, right? Now what I can do is I can go a little bit more fancy. This is an exponential decay. What is NMR? Exponential decay. What is Kraft or what is time domain analysis? Sinusoidal functions of exponential decays. This is also an exponential decay, except this is exponential decay of zero frequency. But there are two components within that exponential decay. Those two components belong to two different T2 stars. And so when I do a T2 star spectrum, which is I'm just plotting the decay rate as a T2 star on the bottom, I'm just taking the same table. I just do the table and then say, don't bother with my frequency. That's zero, I know, because I just said all phases are equal. Frequency has no meaning, but plot the T2 star. And then it plots up and then say, hey, you have two T2 star in there. Here is what, guess what? In this area, there are two T2 star, no CPMG done. I'm able to find both. Purely because I'm working with table, and that table has 4 dimensions. I have a 4-dimensional data already. It's not a 1D, it's a 4D, not in the conventional ND. It's a 4-dimensional information space. And I can look at it whichever way I want. That's the beauty that you have once you work in tabular domain. And this was triggered by a poster. They wanted to actually study what happens when there's a reaction happening as during your acquisition. Now you can do that. You can do that, definitely. Think of laser-induced reactions that you do, and that it happens within a second. Reaction happens within. You can follow that, sure. It doesn't have to be a singlet. It can be any multiplet you want. Overlapped multiplet, sure. All you need to do is first convert that into table and then worry with the table. Don't bother with FT. FT is very, very useful, but going from spectrum to table is where all our challenges historically for the last 50, 60 years. So that's the basics. Don't go from frequency domain data to tabular domain data. Do the other way. You have a potential opportunity. How good it is, I don't know. I just want people to think about different ways of doing it. I have only access to Bayesian, which is Larry's tool that exists in cyberspace, and I download it and then I use it. If I had some other tool, somebody else writes, and then that works better, sure. But the concept of going from time domain to tabular domain to frequency domain makes a lot more sense to me, because it has a lot more potential opportunities that we never thought of that we could do. Imagine, as I said, in this particular example, imagine a reaction as fast as during your acquisition. Equilibrium, that's happening. 2 protons exchanging, that's happening at fast rate. There is an opportunity here to study. So I'm going to skip that. This is a conventional TD-NMR. Actually, this is all water olive mixture. emulsion that you can actually to start. All I'm doing is I'm not doing a Laplace transform. I'm not doing an exponential fit. I'm just telling Bayesian, tell me how many exponentials you have in this. And then it comes back and say, yeah, you have two exponential decay functions. The line width here is an uncertainty, just like frequency. I just call the uncertainty in the T2 star as a line width. And I can do the same thing with sedimentation kinetics. This is a sedimentation kinetics with 24 hours, 50 hours, 168 hours. As it sediments so that you are looking at a much less number of. It's the black lines that you want to look at. This is your solid, the NMR cube, perhaps. So it's going from 4 potential T2 star base and 2 that's becoming narrower and narrower. This is classic T2. So with this, I will stop here. The point I was trying to make is, if we go back to the basics, there are more opportunities that exist that we don't have to rely upon our conventional wisdom. We do have a conventional wisdom. It does help us to think better. But I am challenging you as a benchtop. There's a lot more benchtop can do to the future. I'm challenging the benchtop to think different. So that means let go so you can move forward.
Thank you, Krish. And questions?